so let's look at section 3.2, which is about Euclidean algorithm. So this is a way for finding the greatest common divisor between two integers. We call them m and n. So notice from the core problems, for some of them I've changed them slightly from how the instructions in the book state them. So I've provided the exercise I want you to work as well as the solution for 5, 7, 9, 13, 15, and 17. For the others, you can do them as they're stated in the book at the end of the section for 3.2. So let's start just by thinking about divisors before we think about greatest common divisors. So for example, for the number 24, thinking about numbers that divide 24. So they could be either positive or negative. 1 divides 24, 2, 3, 4, 6, 8, 12, and 24. So both the positive and negative of each of these. So then for 30, same thing, both positive and negative. 1 divides 30, 2, 3, 5, 6, 10, 15, and 30. So now looking for things that show up in both of these lists, integers that divide both 24 and 30. So 1 divides both, 2 divides both, 3 divides both, and 6 also divides both. So both positive and negative, 1, 2, 3, and 6. So the greatest common divisor is the biggest thing that we have on our list. So our greatest common divisor is 6. So for 24 and 30, we probably could have figured that out without listing all of the values, but as we start to get to really large values like 715 and 312, it gets a little bit trickier to tell what the greatest common divisor is going to be, and we don't really want to have to list out all of the divisors every time. So the notation that we'll use here, given integers m and n that are not both 0, so one of them can be 0, just not both, the greatest common divisor of m and n is the largest integer that divides both of the numbers. We write it as GCD and then list the two numbers in parentheses. So we're going to look at one theorem here, and that's our lead up to the actual Euclidean algorithm. So this is called theorem 3.3 in the book. So say we have a, b, c, and q that are all integers, and b is greater than 0. If a is equal to q times b plus c, so that should look familiar from section 3.1, our division algorithm, then the GCD of a and b is equal to the GCD of b and c. So notice where these values are showing up. So it's saying the GCD of a, which is this value here, and b is going to be the same as the GCD of b, so that same b, and c this time. So a proof. Why is it that this works? So let's think about this. So let's use some other letters. Let's let D be the greatest common divisor of A and B. So another way of thinking about this, if D is the greatest common divisor of A and B, it means that D divides both of them. So we could write, we could write our value of A as some constant times D. So D times some constant, we'll call it K1, where K is an integer. And also B is equal to that GCD of D times some constant. We'll call that one K2. So possibly different constants, possibly the same. Now let's let E be the greatest common divisor of B and C. So we could say that B is equal to some constant times E. So E times, we'll call it K3. And also C is equal to E, our greatest common divisor, times some K4. So K1, K2, K3, and K4 are all integers. So remember what we started with. We have that A is equal to Q times B plus C. Well, now I'm going to make some substitutions using what we just wrote above. So in place of B, I'm going to use this definition that we had here, that B is equal to E times K3. So I'm going to have my Q still, but E times K3. And in place of C, I'm going to use this equation that we wrote here. C is equal to E times K4. Well, with a little factoring, we can see that both of these have an E, so we could pull that E out in front, which leaves QK3 plus K4. So what does this tell us? So now A is equal to E times some integer. So a sum of integers is still an integer. This means that E divides A. And we already knew that E divides B from this statement that we had here. So E is a common divisor of both A and B. So we just showed that E divides A. We already knew that E divides B. With E either less than or equal to D, which was the greatest common divisor of A and B. So the greatest common divisor is the biggest one. So we know that E is a common divisor, maybe not the greatest common divisor, so it's either less than or equal to the greatest common divisor. In the same way, so also, if we take that original statement that we had, our division algorithm, and just move some things around a little bit, we could say that C is equal to a negative QB plus A. So just moving that QB term to the other side. And then make some substitutions again, just like we did before. I could replace B, this time I'm going to use the first definitions, with D times K2, and replace that A with D times K1. So some factoring, and we've got D times negative Q K2 plus K1. So just like we said before, so D divides C. We already knew that D divided B, so D is a common divisor of B and C. With D either less than or equal to E, E was the greatest common divisor of B and C. So it follows, if E is less than or equal to D and D is less than or equal to E, it must be that D is equal to E. So we've got that the greatest common divisor of AB is equal to the greatest common divisor of BC. So taking out these pieces from our division algorithm, the GCD of A and B will be equal to the GCD of B and C. So how does this help us out in finding the greatest common divisor of two numbers? Let's take a look at what's called the Euclidean algorithm. So given two non-negative integers m and n that are not both 0, this algorithm is going to compute the greatest common divisor of m and n. So let a and b two integers, both of them greater than 0. We're going to apply the division algorithm repeatedly. So thinking about our division algorithm, what it says that our a, we could write it as some quotient, we'll call it q1, times b plus a remainder, we'll call it r1. The division algorithm guarantees that this remainder, r1, is between 0 and b. So now, since we just showed in our last theorem that the GCD of A and B is equal to the GCD of B and the remainder, I'm now going to think about using the division algorithm on B and R1. So I'm going to take B and find the quotient, we'll call it Q2, that goes with R1, and find a new remainder, R2. So this R2 is now between 0 and R1. And now in the same way, I'm going to look at R1 and R2. R1 is some quotient times R2 plus another remainder, where R3 is between 0 and R2. We could keep going with this process until we get some R, call it sub m minus 1, will be some quotient, m plus 1, times rm plus 0. Eventually, our remainder will turn out to be 0. So since the GCD r sub m and 0 is just r sub m, so anything divides 0. So the greatest common divisor of a number and 0 is always just going to be the number. Then by our theorem on the page before, the GCD of A and B is also going to be this r sub m. So notice what was happening with our numbers. So our B became our new value over here. This R1 came here. R1 became our new value over here. Our remainder became our new value getting multiplied by our quotient. We just keep going like this. The other thing that we want to notice is that these remainders are non-negative and they're decreasing. The decreasing part is important. That's what guarantees that eventually we're going to get down to a remainder of 0. So at some point, it may take a lot of steps, but some finite number of steps will end up with a remainder of 0. The greatest common divisor of some number and 0 is always just our number, and so because of our theorem 3.3, this tells us the GCD of A and B, the values that we started with. So let's pause and move to a new video and try this with some actual numbers.